I can close this. Yeah, okay, perfect. Yeah, thank you, Irene, very much. As Irene just mentioned, I'm Pelayo Peñarroya. I'm ESR 14, and I'm currently working in Deimos Space in the mission analysis and navigation team. Today, I'm going to talk to you about Astrosim, which is a simulation tool for the FLAIR project. So Astrosim is a more general tool that I'm using also for my personal investigation. But in this presentation, I would like to introduce you, or at least to talk about it from the FLAIR perspective. In this presentation, I will be, first of all, giving a bit of context. Then I will proceed to explain a bit the components that compose Astrosim. After that, we will talk about its role in FLAIR. And finally, I will conclude the presentation with the current status of the tool and with the future steps I need to take in the development. So in the context, as I said before, I am an early stage researcher number 14, and my topic is intelligent navigation and control systems for minor celestial body descent and ascent. On the other hand, as Shubham and Carl presented yesterday in the afternoon session, the project working group I'm involved in is FLAIR, which is flexible landing on asteroids using intelligent robotics. This PWG puts together 4 different fields of knowledge, let's say, with the 4 components of the group. First of all, the gravitational dynamics for regular bodies that are studied by Roberto, GNC systems and algorithms, which is myself who is developing them, image-based navigation, which is the contribution from Carl, and robotics, which is kind of the characteristic part of the idea, the concept we had here, which is tackled by Shubham. As you can see from the very titles of the investigations, both projects require a simulation environment for analysis and testing. So we can develop different tools, but in the end, we will need a simulation frame to actually be able to perform this analysis and testing. And this is how Astrosim was born. The idea for Astrosim is to be an orbit simulator focused around small bodies, although it can also propagate or simulate any kind of orbit around any kind of body, as provided a proper definition of the environment. The programming language chosen was Python, and reasons being that no license, or I mean, for some of the libraries in Python, you need to have, or there are some licenses that allow you or not to use them for such and such uses. But most of the times you are able to find very powerful resources where you're not restricted by the license. Then it's also an object-oriented programming language, and this was also something very interesting to me when I first started thinking about how I wanted to structure Astrosim, and I will talk about this a bit more later. The idea, as I said before, is that Astrosim should be a test bench for GNC algorithms. Basically, if we want to try out different combinations of estimation filters with guidance optimization algorithms, and also different control laws altogether, and see how they actually work together, this is the place where these studies or analysis should be performed. And this, in time, also means that the design for such a tool should be modular, because it should allow for the integration of several functionalities, including robotic arms dynamics, trajectory optimization, filtering techniques, actuator instrument definition, or image processing, as we mentioned before. So now let's go a bit more in detail about the description of Astrosim. I hope you're all familiar with Python. On the right side of the screen, if you go to the line, no, I'm kidding. I'm gonna explain it in a much more easy to understand way. So as we mentioned before, one of the key concepts of this presentation was that we wanted to have an object-oriented kind of programming technique, or actually tool. So the first thing that I created when developing this was an object, which is basically a spacecraft. Then on top of this spacecraft, you basically mount dynamics. Yeah, I think I'm gonna have to mute this all. You mount the different dynamics that you want to include in the spacecraft. This includes third body gravitational sources, what degree and order of the coefficients of your central gravity model you want, solar radiation pressure, Also, you mount the instruments that you want to have in your spacecraft. So basically, this could be a camera, 2 cameras, a camera and antenna, a LiDAR, an altimeter, anything you want to define, you basically attach it. And finally, actuators, which include thrusters, reaction wheels, or any kind of, well, in this case, talking about FLAIR, also robotic arms could be included here. And this is basically what you have. So once you have your spacecraft all defined, the only thing you have to do is put it in an environment. So you define your initial conditions for your environment, you define the bodies that are involved in your simulation, you define your starting position, you define your starting epoch, and any parameter that you would think it's fit for or needed for the definition of the simulation. Not only one spacecraft, because we're talking about object-oriented programming, we can define 1, 2, 3, or n different spacecraft. And a very nice feature that this has is that each spacecraft is independent from each other. So you can define spacecrafts with different sets of instruments, different sets of actuators, or even different dynamics, which conceptually might sound a bit counterintuitive, let's say, because if all the spacecraft are, or all pieces of spacecraft are in the same environment, they all should be affected by the same dynamics. But for example, this is very interesting from a mission analysis point of view, since, for example, sometimes you want to try out or to analyze what's the effect of different order in your gravitational model or different gravitational models affecting the propagation of your trajectory. And with this, you can simply clone spacecraft 1 into spacecraft 2, and in spacecraft 2, you set different dynamics affecting the dynamics in there, sorry. And basically what you obtain is in one whole run, 2 different trajectories that you can simply analyze and plot against each other at the end of the simulation, which is something that we engineers like a lot. Once you have all these objects defined, you can call different methods for each of these subjects. This is how Python works. Basically, you have an object and then you have methods. And in this case, methods include propagate, which moves the spacecraft in position, steer, which rotates the spacecraft in attitude, for example, generate eclipse reports, any kind of plots you can think of, generation of ephemeris, and all the things. Once you have defined your spacecraft and you know the methods that you can do, it's very simple to elaborate a scenario chain, as I call it here, where this is an example of a scenario setup, where basically we start by defining some initial conditions, and then basically you have your script where you keep giving commands. No, so one command will be, okay, now take an observation. This could be, for example, take an image with your camera, which is in your instrument suit. Then perform navigation, and with that navigation, optimize the trajectory to get here, so do the guidance. Then propagate with control or without control, so with some errors in the control, for example. After some time, you execute a maneuver. Then navigation and guidance again, even performing a landing. This could be also some sequence. And this is very simple to program once the tool is in place, because you basically have to place in your script the different lines and the different steps that your simulation is gonna have. Now let's talk a bit about Astrosim in FLAIR. So let's put it in context. This is a very similar slide to what my colleagues Carl and Shubham presented yesterday about FLAIR. The members of the group, we all work in different fields. Roberto, for example, is working in dynamic near small bodies and the modeling of these small bodies. Carl is working on visual state estimation and uncertainty, and also in the image rendering for the project. And Shubham is working on the GNC and robotic arm integration, and also in the robotic arm concept itself. I'm working on the development of landing algorithms and on the integration of the GNC plus robotic arm system, and also the dynamics. This would be basically what we call Astrosim. And then from Roberto, I would have to integrate the new gravity models he considers adequate to analyze, and also the gravity model estimation as we get close to the asteroid, or when we perform any kind of experiment. From Carl, the rendered camera images and also the image processing for navigation, which we're currently looking at. And from Shubham, also the robotic actuator so the robotic arm as an actuator, and also the constraint in the end zone conditions. All of these will be integrated in Astrosim, creating what we consider the simulation environment that we need for this project. Now about the current status, these are some plots that we also saw yesterday very quickly. These are results for propagation validation. This includes third body point mass gravity and solar radiation pressures, apart from the main body gravity as well. And these are validated against an also validated tool we have here in Deimos called NAUS. These are trajectories around the Earth, propagated for 14 days, and we can see that the errors in position are in the order of 20 centimeters, and in velocity, centimeters, and in velocity of the order of 1 to the minus 8 meters per second. So very satisfactory results. These are plots generated by the navigation capabilities of Astrosim. Here we can see the typical. This is what we did in the workshop in Madrid, and you can see here the typical curves for the truth versus estimated trajectory, which is only valid for analysis and validation because typically you don't have the true trajectory. And also a very classic plot for the residuals you have. In this case, were azimuth and elevation observations of the asteroid we were orbiting around. Currently, I'm working on integrating the guidance part, which is what you see here. We are basically implementing an optimization algorithm based on IPOPT, which is a classic tool for engineering in terms of optimization. And the study case where I validated the problem setup was a moon landing scenario. Here we see in the third plot on the right side, the classical bang-bang control, which is very well known for these kind of scenarios. And we see that the endpoint conditions, I hope you see the mouse here, end at 0 meters altitude and 0 meters per second in velocity. Here you see a rough plot of the position. The fact that so this has been conceptually developed and now has to be implemented into a tool, and this is not straightforward because the implementation in tool requires that all of these parameters, for example, the thrust profile or these kind of things, is in very small detail implemented with, for example, the definition of the actuators and the definition of the environment. So this is a process that is a bit lengthy to implement, but I'm getting close to finalizing it, which would be the beginning of the next part, which would be what I'm going to talk about now. Here we can see a block diagram of how the tool works, basically. So if we consider the GNC simulator as a black box for now, the general process of the information here is basically the GNC simulator performs its duties and tells the actuators what to do. The actuators are mounted on the spacecraft propagator, which in turn has some dynamics implemented or included inside. And this basically propagates the spacecraft in position and altitude if needed. With that, we will have an asteroid surface image generator from where we could get an image. And with that, an image processing we would perform the landing site state estimator that would be the observation that the GNC simulator takes as an input. Now looking into the GNC simulator more in detail, we see that this observation would go into the navigation, probably more observations, but this is a simplified version. Goes into the navigation where we get a spacecraft estimate state. With that, we can perform the guidance and the planned trajectory is obtained. With that, we have basically the thrust profile, and this completes the whole loop in the GNC simulation. As I mentioned before, the spacecraft propagator has been already validated and it's in place. Same goes for navigation. I mean, there's always possibility to include more and more features, like different kinds of observations, different instruments, different error profiles, anything, but the whole skeleton is already there. Guidance, as I mentioned before, is also being implemented right now. And then what's missing would be the integration part from the integration of the pieces of code that my colleagues in FLAIR are developing. This would be Carl's part. This would be Shubham's part with the robotic arm, and the dynamics inside the propagation would be Roberto's part. And this is basically what's separating us at the moment from obtaining some results that we can hopefully show off in the final presentation of the FLAIR project. So with that, I would conclude my presentation. Thank you very much. And if you have any questions, of course, feel free to ask. Thanks.